Welcome to the first lecture on inverse trigonometric functions. In the previous 7 lectures, we discussed trigonometric functions like sin x, cosine x, cot x, tan x, cosec x and sec x. From this lecture onwards, we are going to define their inverses, and we will also discuss the identities between these inverse functions. Let us take the case of sin x. So, as we know from our previous lectures, the sin x function has a domain which is the set of all real numbers, and the range is all numbers between -1 and +1. What this means is that if we take any real value x, then sin of x will definitely belong to the closed interval -1 to +1. The next question is, can we define the inverse function of the sin function? So, by inverse function, what I mean to say is that if we take any y belonging to -1 to +1, the question is, will there exist a unique x belonging to R such that sin of x is equal to this y. So, this is the basic question that we are asking. So, let us obviously, because sin x, as we know, is a periodic function, this is not true. So, here on this slide I have plotted the graph of sin x on the vertical axis, x is on the horizontal axis, and let us say that we have y equal to half, and we are trying to find out all those x such that sin x is equal to half. So, what we do is we draw a horizontal line here which is parallel to the x axis and which is at a displacement of half on the positive side on the y axis. And then what we see is that there are many values of x, for example, this value and this value here and this value of x. So, all these values of x are such that sin of x is equal to half, and there are infinitely many actually. So, this therefore, from this we know that we cannot find a unique x such that sin x is equal to half, and therefore, in general, as of now it appears that it will be difficult to define the inverse of the sin function. However, we can still define its inverse. For that, we need to take up a smaller simpler example. So, on this slide we have a plot of the function f x equal to x square. So, y equal to x square is plotted on the vertical axis, x is on the horizontal axis, and this is the blue dotted curve is the curve for y equal to x square. So, the function f is defined from the set of all real numbers to the set of all non-negative real numbers, which I denote by R plus. Now, as you can see here, for any value of y in the range of this function f, so let us take for example, this is y equal to 1. So, for y equal to 1, we see that there are two values of x, one is x equal to +1, and then there is another value of x which is x equal to -1. So, for both x equal to -1 and x equal to +1, we get y equal to 1, and therefore, again there is no unique x such that f x equal to x square is 1, because for both these x equal to -1 and +1 we get y equal to 1, and therefore, there is no unique x, which means that again to define the inverse of this function f x equal to x square appears difficult. So, one usual trick is that, so we try to restrict and define a new function f which is the same as the old function. So, we will still have f x equal to x square, but then we will restrict the domain of this function f from the set of all real numbers to a subset of the set of all real numbers. So, let us say that we restrict this function f in this case to this following subset. Let us say that we restrict it to the set of all. So, we take this set which is so from 0 to all to infinity. So, we say that we define a new function f prime which is from r plus. So, r plus is essentially this interval from 0 to infinity. So, we define a new function f prime from r plus to r plus, and f prime of x is again x square. Right. So, f prime is again f prime x is x square, which is the same as what we had before. It is just that the domain now has been restricted from r to r plus. But the advantage of doing this restriction is, first of all, that by restricting the domain from r to r plus, we still see that the entire range of the function is still the same. So, earlier the range of this function, the previous function f was r plus, because f x equal to x square, and since x square can only be non-negative, the range of the previous function was r plus. Even now, when we restrict the domain of this function f from r to r plus, even now the domain will still be r plus, because all non-negative numbers will be in the range of this new function f prime. So, what we see is that we have restricted the domain in such a way that the range of the function is still the same. So, we are not changing the range of the function. But the important thing that we have done here is that by doing this restriction of the domain, now what we see is that, so I am plotting the graph of this function f prime in red. So, I essentially only consider the graph of f x equal to x square only on the positive side of the horizontal axis. So, this curve in red is the graph for the new function f prime. And now, if we take any value of, let us say we take, so this is y equal to 1, 2, 3, let us say 4 here. So, if we take y equal to 4, then what we see is that with the restricted domain, there is only one unique value of x, which is x equal to 2, for which f prime x is equal to 4. In fact, even for y equal to 1, for the restricted function, for the function f prime with the restricted domain, there will be only one unique solution, which is x equal to plus 1. And this happens because we have restricted the domain of the function from r to r plus. And therefore, now there is uniqueness, because we can take any other y, we can take this y for example, let us say this is some value of y. So, even for this y, this is the unique x, this is the unique x such that f prime of x, which is x square, is equal to this y. And therefore, for this restricted function f prime, it is now possible to define the inverse meaningfully. For this f prime function, the inverse will be, let us say g, which is from r plus to r plus, and for any y belonging to r plus, the inverse will be g of y will be equal to square root of y, where this is the positive square root of y. So, this is how we define g. So, many times you will write g also as, it is many times written as f prime inverse. So, So, we use this superscript on the name of the original function to whose inverse we are defining. So, f prime inverse, or many times people do not even write like this, they just write f prime inverse is from r plus to r plus, and f prime inverse of y for any y belonging to the domain of f prime, forgot a prime here, f prime inverse of y is equal to the positive square root of y. So, now we are going to use the same method of restricting the domain of the function such that the range does not get altered, but then the inverse should be meaningfully defined. So, the whole trick here is to restrict the domain of the function. For example, even in this case, if we let us say restrict the domain instead of r plus, if we restrict the domain to let us say some interval -2 to +2, then this will not work, because if we restrict the domain from -2 to +2, then the range of this function will only be from 0 to, so let us say that we restrict it to -2 to +2. So, if we restrict it to -2 to +2, then the range of the function will be only from 0 to 4, right, whereas the range of the original function was the set of all non-negative numbers, and that is not the same as this range 0 to 4, right. So, this is not a meaningful restriction, because we should try to restrict the domain of the function in such a way that the range does not get altered, the range is still the same. So, we will now use this technique to restrict the domain of trigonometric functions, so that we can define their inverse meaningfully. So, we go back again to the y equal to sin x function, and now we know that the range of the sin x function is between -1 and +1, and if we see here, if we restrict, let us say, the domain of the sin x function, let us say we restrict it from -π/2 to +π/2. So, we restrict the domain of the sin x function to the interval, to the closed interval -π/2 to +π/2. So, by doing this restriction, we see that the curve for the restricted function will be the solid red curve, which I am going to draw now. So, it will be this. So, this is the curve for the restricted sin x function, where the domain has been restricted to -π/2 to +π/2. And as we can see here, even after this restriction, all the possible values are there, because if we try to follow this curve, then for example, here it is -1, and then as we go in this direction, the values of sin x go from -1 to 0 continuously, and then further, if we go further towards further from 0 to +1, and therefore, even after this restriction, the range of the sin x function is still -1 to +1. Additionally, what we also see is that if we take any value of y in the range -1 to +1, so let us say we take this y here, so y equal to -half. So, if we take y equal to -half, then we see that there is only a unique value of x in this restricted domain, such that sin of x is equal to -half, because as you can see in this restricted domain, this sin x function when restricted to this domain is strictly monotonically increasing function of x, and therefore, there is for any y that we take in this range -1 to +1, there will be a unique value of x in this interval, such that sin of that x will be equal to this y. So, for example, we see here that for y equal to -half, this value of x is equal to, so this value of x is equal to -30 degrees or -π/6. and therefore, we say that sine, so we have sine of minus pi by 6 is equal to minus half, and from here then we write that sine inverse of minus half is minus pi by 6. So, now that we have restricted the domain of the sine function to the closed interval between minus pi by 2 and plus pi by 2, we are in a position to define its inverse uniquely and meaningfully. So, in this graph we are going to plot the sine inverse function whose domain will be the interval, the closed interval between minus 1 and plus 1, and the range will obviously be the closed interval between minus pi by 2 and plus pi by 2. Here is a table of sin x versus sin x values which will help us to plot this graph. So, let us start with minus 1. So, we know that, so this is known to us that sine of minus pi by 2 is equal to minus 1. So, from here we can say that sine inverse of minus 1 is equal to minus pi over 2. So, sine inverse of minus 1. So, sine inverse of y equal to minus 1. So, y equal to minus 1 is here, and sine inverse of minus 1 is minus pi by 2, minus pi by 2 is over here. So, we essentially have this point on the, so this is minus 1 and this is minus pi by 2. So, sine inverse of minus 1 is minus pi by 2. So, we basically have this point on the graph, and then moving further ahead we have sine of minus pi by 3. So, sine of minus pi by 3 which is sine of minus 60 degrees is equal to minus square root of 3 over 2, and from there we can write that sine inverse of minus root 3 over 2 is minus pi over 3. So, sine inverse of y equal to minus root 3 over 2. So, this is 4 units and minus root 3 over 2 is around minus 0.86. So, that will be approximately somewhere here, and then minus pi by 3. So, this is minus pi by 2. So, 2/3 of this will be minus pi by 3. Since this is 6 units, it will be somewhere here, and therefore, this is the point on the graph that we get. So, similarly, from this graph we can also show that sine inverse of minus sine inverse of minus 1 over square root of 2 will be equal to sine inverse of minus 1 over square root of 2 will be minus pi by 4. So, minus 1 over square root of 2 is minus 0.7, which is somewhere here, and minus pi by 4 is half of this, which is somewhere there. So, this and this is going to meet over here, and then sine of minus pi by 6, which is minus 30 degrees, is minus half, and minus half is here. Minus pi by 6 is 1/3 of this thing, which is over here. So, we get another point like this, and of course, sine inverse of 0 will be 0, which is here, and we will have a symmetrically similar thing on the for positive values of y. So, we will have this point for because sine inverse of 1 is equal to pi by 2, and then for plus root 3 by 2 we have sine inverse of root 3 by 2 equal to pi by 3, which is over here. So, this and then this will get us this point, and similarly for pi over 4 we are going to get this point here, and then for pi over 6 we have this point here. So, if we join all these dots, we get the So, this dotted red curve is the graph for sine inverse of y. Similarly, for cos y also we see that if we do not restrict the domain of cos function, then again the reason is that because it's a periodic function, what will happen is that with the domain as the whole real line, we cannot define its inverse meaningfully, because any value of y that we take in the range of this cos function, there will be many different values of x for which cos x will be equal to that y. But we see that if we, let us say, restrict the just like the sine function, if we restrict the cosine function, the domain of the cosine function to the interval from 0 to pi. So, we only consider from 0 to pi. So, 0 to pi, the closed interval between 0 to pi. If we restrict the cos function to this subset of the real line, then the graph of the cos function will be like this. And again what we see is that just like for the case of the sine function, this the entire range is covered even if we restrict the domain to 0 to pi. The range of the cosine function when restricted to this 0 to pi interval is still between 1 and minus 1, all values between 1 and minus 1, because this red curve is continuous between 1 and minus 1. So, we can start from 1 here, and as we go along the curve we reach a value of 0 at pi by 2, and then further down we go all the way till minus 1 when x equal to pi. So, even by restricting the domain of the cos function to 0 to pi, the entire range is still the same. Further, what we see is that if we take any value of y, let us say we take y equal to, let us say, half over here. So, for y equal to half, if we look at the original cos function whose domain was the entire real line, then we will have many different values of x here, and then another value here, and another value here, similarly another value here, and here also, and so infinitely many values of x for which cos x is equal to half. But when we restrict the domain to 0 to pi, what we will see is that there is only one value of x, one unique value of x, which is in this case, in this example, it is pi by 3 or 60 degrees, because cos of 60 degrees is equal to half. And therefore, what we see is, so it is not just true for y equal to half, we take any other y in the interval minus 1 to plus 1, which is the range of the cos function. What we will see is that there will always be a unique x in this restricted domain, such that cos of that x will be equal to this y. And of course, it is also visibly clear, because as we can see, this function, cos function, when restricted to this domain, when restricted to 0 to pi, the graph is monotonically decreasing, and therefore, for any value of y that we take, there will always be a unique x in this interval. And therefore, the inverse of the cos function can now be uniquely, meaningfully defined. So, just like for the sine function, we have the inverse of the cos function from minus 1 to plus 1 being the domain, and the range is the closed interval 0 to pi. And again here we have a table of values. So, just as we did for the sine function, we start with so we have cos of pi equal to minus 1, and therefore cos inverse of minus 1 will be equal to pi. So, cos inverse of y equal to minus 1 is here, will be equal to pi. Pi is here, so we have this point on the graph. Okay. And then let us take here. So, here we have cos of 3 pi over 4 is equal to, cos of 3 pi over 4 is equal to minus 1 upon square root of 2, and from here what we get is that cos inverse of minus 1 over square root of 2 will be equal to 3 pi over 4. So, minus 1, so y equal to minus 1 over square root of 2 is somewhere here, and 3 pi by 4 is basically 3/4 of, so this is 9 units. So, 3/4 will be somewhere around 6 3/4 of units, 3, 4, 5, 6 and somewhere there. So, the point that we have is this point on the graph. And similarly, when we go further ahead, we see that for cos x equal to minus half when x is equal to 2 pi by 3, and therefore, cos inverse of minus half. So, cos inverse of y equal to minus half. So, y equal to minus half is here. So, cos inverse of minus half will be equal to 2 pi by 3, which is 2/3 of this whole range, which is equal to 6 little squares. So, that comes over here. So far we have gotten this part of the cos inverse curve, which I am showing with a dotted line. And then further we know that cos of pi by 2 is 0, and therefore, cos inverse of 0 will be pi by 2. So, cos inverse of 0 will be pi by 2 is half of this entire range, which will be somewhere here. And then we will have a similar symmetric curve about this line on the for positive values of y. So, for example, for we know that cos of 0 is 1, and therefore, cos inverse of 1 will be 0. So, which is this point over here, and let us take one more point. So, pi by 3, we know that cos of 60 degrees, which is pi by 3, is equal to half, right. So, therefore, cos inverse of half will be pi by 3. So, cos inverse of y equal to half is here. So, cos inverse of y equal to half is pi by 3, pi by 3 is here. So, we have this point. So, the curve will look something like this, something like that. So, this is the curve for the cos inverse function. So, similarly, we have the other trigonometric functions, and everywhere we have the same problem, that if we just look at the entire domain as we had defined in the previous lectures, it will be difficult to define the inverse meaningfully, and therefore, we have to restrict the domain. For example, for the tan function, the domain is all real numbers except odd multiples of pi by 2. The reason is that at odd multiples of pi by 2, the tan function becomes unbounded. So, this is the graph of the tan function. On the x axis we have x, the vertical axis is tan of x, and the blue dotted curve is the tan x function. And as we can see, this is again a periodic function, it repeats with pi, and therefore, what we can do is that if we restrict the domain of the tan function to the interval between minus pi by 2 to plus pi by 2. So, here we have to take the closed interval. So, this will take the open interval, because so this is the open interval. The open intervals are denoted with a rounded bracket, and the closed, for the closed interval we take a square bracket. So, if we restrict the domain to this open interval, the reason for taking the open interval is because the tan function will become unbounded at minus pi by 2 and plus pi by 2. So, we have to avoid those 2 points. So, all other points in between minus pi by 2 and plus pi by 2 will be the restricted domain of the tan function. And when we restrict the tan function to that domain, the curve for the restricted tan function becomes, I am showing it with the red curve. So, the red curve, as we can see now, first of all, the red curve is going to cover the entire range of the tan function from minus infinity to plus infinity. So therefore, even by restricting the domain of the time function to this open interval between minus pi by 2 and plus pi by 2, what we see is that the range still remains the same as before, which is the set of all real numbers. The interesting thing, however, that happens is that if we take, because we see that this red curve is a monotonically increasing curve, right, and therefore it is clear that if we take any value of y in the range of the tan function, so any real value of y, then what we will see is that there will be always a unique value of x in this interval minus pi by 2 to plus pi by 2. There will be a unique value of x such that tan of x will be equal to that y. So therefore, again for the tan function, it is clear that by restricting the domain to the open interval between minus pi by 2 to plus pi by 2, the inverse of the tan function can be uniquely defined. So on this slide, we again, just like the sine and the cosine function, we plot the graph of the inverse of the tan function. So as we can see, the domain of the tan inverse function is the set of all real numbers. The range, of course, is the open interval between minus pi by 2 and plus pi by 2, as shown here. And let us try to plot the graph now. So as we can see from this table of values here, that first of all tan of 0 is 0. So we know that tan of 0 is 0, and from that it follows that tan inverse of 0 will be equal to 0. So tan inverse of y equal to 0. So tan inverse of y equal to 0 is equal to 0. So in this graph we have y is plotted on the horizontal axis and tan inverse of y is plotted on the vertical axis. So y equal to 0 is this point, and tan inverse of 0 is also 0. So therefore we have this point on the graph of tan inverse. Then we see that tan of pi by 6 is 1 over root 3, and therefore tan inverse of 1 over root 3 will be equal to pi by 6. So tan inverse of 1 over root 3. So 1 over root 3 is should be somewhere over here. So this is y equal to 1 over root 3, and the value of the tan inverse function at y equal to 1 over root 3 will be equal to pi by 6, which is 1/3 of this entire range, which will be somewhere here, will be somewhere there. And then of course we know that tan of pi by 4 is 1, and since tan of pi by 4 equals 1, it follows that tan inverse of 1 will be equal to pi by 4. So tan inverse of y equal to 1 will be pi by 4. So y equal to 1 is here and pi by 4 is here. So we have this point on the graph, right. And similarly we can plot the other points also. So what we will end up getting is some curve like this. But note that the value of the tan inverse will, as the value of y goes to infinity, as it becomes larger and larger, the value of tan inverse on the positive side for the positive values of y, as y goes to infinity, tan inverse y will go to pi by 2, but it will never be equal to pi by 2. It will converge. As you can see, this graph is going towards, so this is the line corresponding to the value of vertical axis being the value on the vertical axis equal to pi by 2. So this dotted curve will never go beyond this solid red line. And similarly on the negative side also, using this table, we can draw the negative side, the curve for negative values of y, and even here the curve that we will get is something like this. So here we have this line which corresponds to tan inverse y which corresponds to minus pi by 2 on the vertical axis, and as y goes to minus infinity, so if as we go in this direction, what happens is that the graph will go, as you can see from here, the graph will go nearer and nearer to this value of minus pi by 2, but it will never exceed that. In fact, tan inverse y will never be equal to minus pi by 2. Similarly, for the cotangent function also that we have here, the cotangent function, the cot x function is nothing but 1 over tan x. So, which is or we can even write it as cos x over sin x. So, cotangent x is equal to cos x over sin of x. And therefore, what you will see is that whenever x is a multiple, an integer multiple of pi, whenever x is an integer multiple of pi, sin of x is 0, and therefore, cotangent of x for x being integer multiples of pi is not well defined. And that is clear from this graph where we have plotted x on the horizontal axis and cot of x on the vertical axis. We can see that at integer multiples of pi, so for example, x equal to 0 or x equal to pi or 2 pi, we see that the graph goes to either plus infinity or minus infinity. So, it becomes unbounded, right. And that is why when the domain of the cot function is defined, it is defined like this. So, for the domain we consider all real values except this set, and this set is precisely what we mean by all integer multiples of pi. So, this is the domain set of the cot function, and of course, the range will be the set of all real numbers, because the cot function will take all real values between minus infinity and plus infinity. And of course, it is also periodic with pi. So, cot x is a periodic function with pi. So, cot x is equal to cot of pi plus x. I mean, if we just consider the same domain which is defined over here, it will be difficult to define the inverse of the cot function. Any value of y that we take here, let us say we take this y. So, this corresponds to y equal to 3 by 2. So, there will be many different values of x, for which cot of x will be equal to this value 3 by 2, and therefore, there is no unique x, and hence with this domain the inverse of the cot function cannot be defined meaningfully, and hence we again have to restrict the domain of the cot function. So, what we do is we restrict the domain to this interval from 0 to pi. So, we take this interval 0 to pi, but we cannot include the points 0 and pi, because the cot function is unbounded, it is not well defined at these two endpoints. So, therefore, we take the open interval between 0 to pi and restrict the domain of the cot function to this open interval. When we restrict it, what we see is that the curve of the cot function restricted to this open interval 0 to pi now becomes what I am drawing with the red solid red curve here. And it is very easy to see now that even after restricting the domain of the cot function to the open interval 0 to pi, what we see is that the range is still from minus infinity to plus infinity. So, the range of the cot function is still the set of all real numbers, even after restricting the domain from this to the open interval 0 to pi. And secondly, it is very easy to also see that the solid curve here is monotonically decreasing, and therefore, if we take any y in the range of the cot function. So, if we take any y, let us take a y here. So, if we take this y, so this y is minus 3 by 2. So, if we take any y, there will be a unique x which is here, which will lie in this restricted domain of the cot function, such that cot of x will be equal to this y. So, this will be true for any value of y that you take, and that is very much clear also, because this cot function is a continuous function in this, it is a continuous function in this restricted domain, and additionally it is monotonically decreasing. And therefore, by restricting the chord function to this domain, we should be able to define its inverse meaningfully. So, we again try to plot the graph for the chord inverse function whose domain will be the set of all real numbers, and the range will be now the restricted domain of the chord function, which is the open interval between 0 to pi. Now, we know that let us start from here. We know that chord of pi by 2 is equal to 0, and therefore, chord inverse of 0 will be equal to pi by 2. So, chord inverse of y equal to 0. So, y equal to 0 is here, will be equal to pi by 2. So, pi by 2 is here. So, we get this point on the graph of chord inverse y. So, here in the graph we have y is plotted on the horizontal axis, and the corresponding chord inverse of y will be plotted on the vertical axis. Similarly, we have chord of pi over 3 equals 1 over square root of 3, and therefore, chord inverse of 1 over square root of 3 will be equal to pi over 3. So, chord inverse of 1 over square root of 3 will be somewhere there, and pi over 3 is somewhere here. So, it will be somewhere there, and then as we, so we will get this point here. So, this is, so this was pi over 2, this is equal to pi over 3, and then as we increase y to more positive values. So, we are going in this direction here. So, for example, chord inverse of square root of 3 will be pi by 6. So, as we increase y, what we will see is that chord inverse will decrease and go towards 0. So, chord inverse, so from here from the table what we see is that chord inverse of square root of 3 is equal to pi by 6. So, square root of 3 will be somewhere here, and pi by 6 is somewhere. So, this is pi by 6. So, we get this point on the curve, right. So, essentially what we have is, so far we have plotted, and it will go like this, but the value as y goes to infinity, chord inverse y will go towards 0, but it will never be equal to 0, right. And then for the negative values of y, what we will see is that we will have a similar type of curve. So, and which can be drawn by looking at the negative values of chord x. So, for example, from here what we will see is that chord inverse of -1, for example, will be equal to 3 pi over 4. So, -1 is over here, and 3 pi over 4 will be, so this is 6 units. So, 3 pi over 4 will be 4.5 units, right. So, it will be somewhere there, somewhere over here. So, this is y equal to -1, and this value here is 3 pi over 4. And then for further even more negative values, what we will see is that the value of the chord inverse function will go towards pi. So, now we are going in this direction. So, as we make the value of, so this is the value of y in this column. As y becomes more and more negative, so from -1 to minus square root of 3, as y becomes more negative, the value of this x is going towards pi. So, what we will have is, so this is pi. So, this curve, the dotted curve will go something like this. So, we finally have the red dotted curve for chord inverse of y. So, as y becomes more and more negative, chord inverse y will tend towards pi, but it will always be less than pi. In fact, it will never be equal to pi. The next function is cosecant function. So, the cosecant function, cosecant of x is, as we know, defined as 1 over sine of x, and it is also a periodic function, trigonometric function, and because it is 1 over sine of x, it will not be meaningfully defined whenever sine x is equal to 0. So, therefore, whenever x is an integer multiple of pi, cosecant of x is not meaningfully defined, and therefore, the domain of the cosecant function is the set of all real numbers except integer multiples of pi. So, that is the domain of cosecant x. And for the range, what we see is that because cosecant x is 1 over sine x, and sine, the range of sine x is the all values between -1 and +1, what will happen is that 1 over sine x will take all values outside the interval -1 to +1. So, and that is very much clear from this graph where we have x on the horizontal axis and we have cosecant of x on the vertical axis. As we can see, the blue dotted curve will never take any value between -1 and +1, and this is because it is 1 over sine x, and sine x takes values between -1 and +1, and therefore, the range of the cosecant function is the set of all real numbers except this range -1 to +1. And therefore, now with because it is still periodic, as we can see, it is still a periodic function, cosecant x is a periodic function of x. If we have this as the domain, we still cannot define the inverse of the cosecant function meaningfully, and therefore, we need to restrict the domain of the cosecant function as we have done for the other previous trigonometric functions. So, in this case, one possible choice is that we consider the interval minus pi by 2 to plus pi by 2 except the point 0. So, we are going to restrict the domain of the cosecant function to the closed interval minus pi by 2 to plus pi by 2, but except the point 0, because at x equal to 0, cosecant of x is not meaningfully defined because it becomes unbounded. So, by restricting the cosecant function to this set or this subset of the real line, the restricted cosecant function, the graph of the restricted cosecant function will look something like this. So, I am drawing it with the solid red curve here, and as we can see, even by restricting the domain of the cosecant function to this interval, we see that all the range of the restricted cosecant function is still the same thing, which is all real values except -1 to +1, because it cannot take any value between -1 to +1 anyways, but apart from this range of values, it does take all other possible values, because for the interval between minus pi by 2 and 0, if we start from here, so this value over here is this is -1, and if we go like this, then we see that the curve is continuous, and starting from -1 it goes all the way till -infinity. And similarly, if we start from here, then this value is +1, and if we go like this, the curve is again continuous, and it goes from, the value goes from 1 to infinity. So, we have values going from 1 to infinity and then from -1 to -infinity, which is basically the same range. So, even by restricting the domain to this subset of the real line, the range of the cosecant function is still the same, it still remains the same. And additionally, what we also see is that if we take any y, so let us take any y in this range set. So, let us say that we take this particular value of y here. So, this value of y corresponds to 2.5. So, this is y equal to 2.5. So, for this what we see is that there is exactly one unique value of x, which is here, such that cosecant of this value is equal to 2.5, and of course, this value lies in the restricted domain. If we had not restricted the domain, then there would have been many other values, for example, this value of x, or for example, this value of x, or this value of x. So, there would have been infinitely many different other x values of x, such that cosecant of x would have been 2.5, and therefore, there is no unique value as such. But when we restrict the domain to this interval, we see that for any value of y in this range, there will always be a unique x. There will always be a unique x in the restricted domain, such that cosecant of that x will be equal to y, that value of y. And therefore, again by doing this restriction, we should be able to meaningfully define the inverse of the cosecant function, which I have will try to plot it in this slide here, and this can be just done just similar to what we have been doing for the other functions, and I will quickly show it to you how it looks. So, this is how it looks. So, again using the table we can plot. So, what we have is we have y on the horizontal axis and cosecant inverse of y on the vertical axis. The domain of the cosecant inverse function will be the range of the cosecant function. So, the domain of the cosecant inverse function is all real numbers except the interval -1 to +1, and the range of the cosecant inverse function will be the modified or the restricted domain of the cosecant function that we saw on the previous slide, which is the closed interval -π/2 to +π/2 except the point 0. And then again using this table of values, so the red curve here and here is what is the graph of the cosecant inverse function, and as we can see as y becomes more and more positive, the value of cosecant inverse will go towards this value of 0. So, this curve, red curve here will always be above the horizontal axis on the positive side, and for negative values of y, the red curve will always be below the horizontal axis. So, I mean this part of the curve. And similarly, the secant function will have a similar problem, and for the secant function also we need to define the inverse of the secant function meaningfully. Just like the other trigonometric functions, we have to also restrict its domain, because secant of x is equal to 1 over cos of x, and we know that cos of x is 0 whenever x is a odd multiple of π/2. So, therefore, the domain set of the secant function is defined to be the set of all real numbers except odd multiples of π/2, because at odd multiples of π/2 secant of x is not well defined, as can also be seen from this graph, where we have x on the horizontal axis and secant of x on the vertical axis. And what we see is again the secant function is also periodic, and the range, as we can see, is that because secant of x is 1 over cos x, and cos x is between -1 and +1. So, what happens is that the range of the secant function is the entire real line, which is the entire vertical axis here, except this interval between -1 and +1. So, that is this range. And just like the other trigonometric functions, we again have the same problem, that because secant function is periodic, with this domain, with this as a domain, we cannot define the inverse meaningfully, and therefore, we need to restrict the domain of the secant function also. So, what we do is that we restrict the domain between 0 and pi. So, we take the restricted domain to be the closed interval between 0 to pi, but as we can see, we should not have the point x equal to π/2, and the reason is because at x equal to π/2 secant of x is unbounded, it is not well defined, right. So, the modified domain will be 0 to pi interval except the point π/2, and the graph of the secant function will then be what I am drawing with the red curve. So, this will be the graph of the secant function when the domain is restricted to this interval except pi by 2, and as we can see the range even after this restriction of the domain is still the same. It is still all real values except the interval -1 to +1, right. So, all values are there except -1 to +1, and also what we see is that for if we take any value of y, then we can always, so if we take any value of y, there will be a unique value of x such that secant of x is equal to y, and that value of x will be in this interval, and therefore, by this restriction we can meaningfully define the inverse of the secant function, which I am defining here. So, on this graph we have y on the horizontal axis, and secant inverse is plotted on the vertical axis, and as we can see, we are again going to make the use of the table values for x versus secant x. The secant inverse function is defined from the this will be the domain, which is basically the range of the secant function, and the range of the secant inverse function will be the restricted domain of the secant function, which is 0 to pi except the point pi by 2. And this is what we get. So, in this lecture we had initially tried to define the inverse of the trigonometric functions, but we immediately ran into a problem because the trigonometric functions are most all of them are periodic, and therefore, with their normal definition of their domains, it is difficult to define their inverses meaningfully. And but then what we saw was that if we restrict the domain of these functions, we can define their inverses meaningfully. So, in the next class we will take all these, we will try to define and prove a lot of identities and relations between these 6 inverse trigonometric functions that we defined in today's class. Thank you.